So hello dear students. Now in this particular unit or subunit, we are going to discuss the interaction of radiation with matter, and in particular we are going to talk about interaction of radiation, that is beta rays, with matter. That is beta rays, when they enter the matter, how they interact with the surrounding medium. That would be the point of discussion in this particular subunit. So electrons interact with matter through Coulomb scattering. So basic interaction mechanism of electrons in matter is Coulomb scattering, but since electrons are very light, so the interaction uh, process is a bit different from the heavy charge particles. The heavy charge particle interaction is a little different from the interaction of electrons with matter, and in that case, since electrons are moving with a very high speed because they are light, so when they come out of our nucleus, which is radioactive, they are basically relativistic. So the relativistic speed also modifies the interaction mechanism, and also because they are very light, so when they collide with the other electrons, they suffer large deflection by collision, and therefore they follow an erratic path. So basically, when an electron strikes another electron, it is deflected to a very high degree, and so when it moves through the medium, it follows an erratic or a zigzag path, and therefore it is difficult to find the range of the particle because the path is very zigzag and curvy and erratic. In a head-on collision, a large portion of energy is transferred to the struck electrons. So the struck electron gains a lot of energy from the incoming electron because both the particles are of the same mass, so there is a large transfer of energy and momentum in the process. And then because the electrons suffer a large deflection, you can say they are suffering a very large acceleration, and accelerated particles must radiate electromagnetic energy. So that is the reason why electrons lose energy through this radiation, which is known as Bremsstrahlung radiation or braking radiation. So these are the few differences which are not present in the case of heavy charge particles when they interact with matter. So different type of scattering processes are possible. Number one is the elastic scattering, in which an incident electron interacts with the atomic nuclei or bound electron, but no energy is lost. But the momentum is transferred. There is a transfer of momentum, but energy is not lost. So the outgoing electron changes its direction to a high degree, but retains its energy. Then the next kind of scattering is possible, which is inelastic scattering, in which the incident electron loses energy by excitation or ionizing the material. So basically, it interacts with the electrons of the atom and tries to ionize or excite that atom. And the processes which are involved is, number one is the ionization process, in which the electrons are ejected out of the atom and the atom transforms into an ion. Then this excitation is also possible, in which the atom does not transform into an ion, but the atom changes its state from a ground state to the excited state without ionization. Then Bremsstrahlung radiation is also possible, in which a high energy electron decelerates in Coulomb field of the nucleus and starts emitting X-rays. And then there are plasmon excitations, in which the lattice structure absorbs the energy and a collective oscillation of the valence electrons is possible. And that kind of thing is particularly in the metal. Metals actually show this kind of excitation, in which a collective oscillation of all the valence electrons present inside the metal, that oscillation starts taking place. So that kind of thing is called a plasmon excitation. So these are the different types of inelastic scattering that are possible. Then an important aspect in the scattering process is the production of secondary electrons. That is, when the incident high energy electron transfers energy to the atomic electron, which are ejected out from the surface. So those electrons also produce secondary electrons. So the electrons which are coming out from the atom, they strike other electrons, and those secondary electrons are produced in a kind of a chain reaction, and those some of them also are ejected from the surface of the material. Then you have backscattering, in which incident electrons are deflected back out of the material after multiple scattering events. That is, in which the scattering takes place in a multiple step, and the incident electron basically changes its direction at an angle of 180 degrees and backscatters to the opposite direction, and that kind of scattering is also possible. Now, of course, the interaction of electrons in matter is described by what is known as the Bethe-Bloch formula for electrons in matter. And in this formula, we again have two types of losses. One is the radiative loss, and the other one is the collisional energy loss. So the radiational loss, which is the loss due to Bremsstrahlung radiation, that is also possible, and where here we are showing the collisional loss, in which the electron collides with another electron and in the process loses its energy. In that case, the stopping power for the collision, that is minus dE by dx, as I have described the stopping power in the previous subunit. So you can look at that subunit to understand the definition of the stopping power. But briefly stated, it is defined by the rate of change of energy per unit length inside the material. That is, if the electrons are traveling a unit length, how much energy do they lose during this transfer, or during this process of covering 1 unit length, how much energy is used. That is given by dE by dx, and collisional means that it is the stopping power for the collisional energy, that is the energy lost during collisions. So it is again given by a Bethe-Bloch formula of the type Kz divided by A beta square into ln gamma square MEC T max divided by 2I square plus phi of gamma plus minus delta, where K is the constant, Z is the atomic number of the absorber, A is the atomic mass of the absorber, V beta is V by C, where V is the velocity of the electron, gamma is under root 1 minus beta square, M is the mass of the electron, T max is the maximum energy transfer in the collision, I is the mean excitation potential, that is the potential you require to ionize or excite the atoms inside the material. So the mean of that is, there are different excitation potentials because there are different energy levels and different types of atoms present inside the material with different energy levels. So the mean of all those excitation level would be given by I. Similarly, phi is the correction for indistinguishable electrons, which is there because the electrons are indistinguishable. So when they collide, after collision, the outgoing electron cannot be distinguished from the struck electron. So the electron that is struck by the incoming electron and the outgoing electron, they are indistinguishable because they are identical. So the outgoing electron cannot be considered to be the incoming electron only. It can be either the struck electron or the incoming electron, because both the electrons are indistinguishable. So that is the reason that according to the Pauli's exclusion principle, we have to add a correction due to the indistinguishability of the electrons. Then delta is the density correction, which is important at high energies. So these kind of terms which are given here are present in the Bethe-Bloch formula for electron in matter, from which you can calculate the stopping power of the electron as a function of velocity or energy, as whatever you wish to. So you can understand how the energy is lost inside the material and how it interacts and loses its energy in the material. Then, of course, you have the radiation loss, which is called as Bremsstrahlung. So, at high energies, radiative loss becomes significant. Why it becomes significant only at high energies? Because the the deceleration process is uh, produces significant energy only at higher energies. So, the significant energy radiation or the would only be produced when the particle which is deaccelerating, it is having a very high energy, a relativistic energy. So it is given by E by x naught. Simply E is the radiation of the incident electron and x naught is a parameter which is called the radiation length of the material, which is a characteristic constant. So this is a simplified equation for the radiative energy loss. So it is just giving a simple expression which tells you what would be the stopping power or the radiation energy loss, uh, and it would be proportional to the energy of the particle. Similarly, as you see, the total energy loss actually would be the sum of the collisional energy loss plus the radiative energy loss. So the rate of energy loss per unit length total is the sum of the rate of energy loss due to collision plus the rate of energy loss per unit length due to radiation. Now, what is important is at low energies, collisional loss dominates, whereas at high energies, radiative loss dominates. So here what is shown is the graph is shown between the energy of the electron or the kinetic energy of the incoming electron versus the rate of change of energy per unit length or the stopping power, and it is divided by one by rho. The dE by dx is divided by rho to normalize, because as I have already discussed in the earlier subunit, why it is divided by rho, so that because this dE by dx depends upon the rho itself. So for different materials, like here in this case lead, aluminium and air, so these materials will have almost the same energy loss within the same kind of scale, and they will not vary very largely with respect to each other when we divide by the density of the material. So we divide the stopping power by the density of the material to get this graph. So on the y-axis we have d by dx divided by rho, and on the x-axis we have t, or the kinetic energy, and it's a log scale. And at the dotted lines show the radiative energy loss, and the solid line shows the collisional energy loss. So you can see that the radiative energy loss is small compared to the uh, collisional energy loss uh, at lower energies, but at higher energies the radiative energy loss increases and almost becomes equal to the collisional energy loss. And you can see that the energy loss does not vary very highly with energy, and also the materials are, because of the division with the rho, the energy loss is also not very different for different materials. So because of this reason, we can find out the stopping power or the range, rather, because from the stopping power you can calculate the range by integrating the inverse of the stopping power with energy. So dx by d into de integrated from t max to 0, that gives you the, basically that gives you the range. So that range can be calculated from the stopping power, and that range, because of the previous slide, you can see it does not change when the materials are changing. If you normalize it by multiplying the range with uh, density, so you divide the stopping power with density, and in process actually you are multiplying the range with density. So when you multiply the range with density, you get the range in the units of gram per centimeter square, because range is in the units of centimeter, and when you multiply it by density the unit becomes grams per centimeter square. And in that units, if you calculate the range and plot it with respect to energy, then you see that almost for the two different materials, one is air and another is aluminium, which are highly different from each other with large energy differences and density differences. But even then, the range for both of them are almost similar. And of course, the range increases with energy. So if the energy of the incoming electron is large, that it is able to penetrate large distances inside the material. So the radiative term is significant, as we have seen, only in the high energy range and in heavy metals, because for radiative energy loss, the vicinity of a charged nucleus is required because of the conservation of energy and momentum principle. So any accelerating electron is going to radiate when it deaccelerates in the vicinity of a charged nucleus. So generally heavy materials would be very important in the case of Bremsstrahlung radiation, and also at high energies, because Bremsstrahlung radiation takes place at high energies. As we have seen in figure 1, the relative contribution of air, aluminium and lead is shown, and the radiative contribution is small, and the variation of the radiative contribution, and also the collisional losses with electron is very small. The variation of these losses with respect to energy is also not varying that much. The variation is small. Though the calculation of the range, as I have told you, can be done with the help of integrating the Bethe-Bloch equation over the path of the electrons. So you integrate the Bethe-Bloch equation, that you integrate dE by dx with respect to the total path to get the mean range or the mean path length of the radiation or the electron which are traveling in the medium. But the problem with this integration is that the random nature of the path, it is difficult process because the path is erratic and zigzag. This kind of process is not very simple because the path is very erratic and very topsy-turvy. It is not a straight line, which is again a very different thing to what we see in the case of heavy charge ions, in which case the paths are almost straight lines. So what we do is we use empirical data. So what we experimentally measure the path lengths by using different slabs of different thicknesses and finding out the number of electrons that pass through a slab of a particular thickness. From there, with different thicknesses, we one by one, and when we find that no electron is passing through the material for a particular thickness of a material, then that thickness would be taken as the path length or the range of that material for electrons. So we use empirical data on absorption of beams of monoenergetic electrons to generate the range energy relationship for electrons. So the figure in the figure shown, the number 2 figure shown previously, as you can look back by going back to the video to a few minutes earlier that I've shown earlier, the monoenergic electrons generate the energy range relationship, which I've shown in that figure, and that you can also calculate for other materials from that graph, since you know that the variation with the type of material changing that variation is not large. As I've shown you earlier, the aluminium and air are almost having very identical range energy relationships. So from this you get this idea that you can calculate the range of any particular material, that is range of electrons or beta rays for a particular energy for any material can be calculated by finding out the range of electrons for the same energy in air or aluminium, and then multiplying that range with the new density of that material that we are talking about. So the new material with the density of that material, when you multiply it by the range for let us say air, and divide it by the range of the air, so from there you can calculate or estimate the range for any particular material. So I think you have understood how to calculate the range. What you have to do is you just have to know the range, actual range in any particular material. For one material, if you know, then you can find out the range for any other material by using the density of that material.